In this lab, I will analyze the motion of a star and calculate the mass of the black hole that it orbits. A star is observed moving in the xy plane. No objects are seen nearby to exert a force on it, so according to Newton's first law, it should move in a straight line at a constant speed. However, its motion is elliptical, so we theorize that some unseen object is causing this, namely a black hole. In this video, first I will use the fundamental principle, Newton's second law, to calculate the net force on the star. Second, I will use the law of universal gravitation to estimate the mass of the black hole. Here is the information we are given to start with. The mass of the star is known, and we have a list of data of its location as it moves. We also know the location of the black hole. Also, we know that the force of the black hole is the only force acting on the star. Therefore, the force of its gravity is equal to the net force. To start out, we need to calculate the average velocity as the star moves between any 2 points. Average velocity is equal to the change in position divided by the change in time. The change in the x component and the change in the y component are equal to the difference between two of the given data points. A 0 is used for the third component because the star does not move relative to the z-axis. Delta t here is equal to 86,400 seconds. This is Newton's second law. F net is equal to dp dt, which is equal to the change in momentum divided by the change in time. Now that we have calculated velocity, we can find momentum and use this to find the net force on the star. Now we use the law of universal gravitation to find the mass. G here is a physical constant. We also know the mass of the star, m1. Fg is the magnitude of the gravitational force, that is, the force the star and the black hole exert on each other. In this case, Fg is also equal to F net. R is the distance between the star and the black hole. The position data are used to find both of these values. M2, the mass of the black hole, is the only unknown here, so we can find the mass by solving this equation for M2. Then F net, the value found in the previous step using Newton's law, is inserted for Fg. The estimated mass will be about the same no matter which given data points we use. Once we know the mass, we can use the same process in reverse to predict the portion of the orbit that is not part of the given data. Typically, F net is used to predict motion, and dp dt is calculated by observing motion. But Newton's second law states that these two values are equal, so either one can be used to find the other. This also means that F net parallel is equal to dp dt parallel, and F net perpendicular is equal to dp dt perpendicular. This VPython model uses arrows to represent F net and its components. F net is red, F net parallel is blue, and F net perpendicular is green. F net parallel is parallel to the star's current momentum and is the component of the force that causes the star to speed up or slow down. F net perpendicular is perpendicular to the star's momentum, and it is always the component that causes the star to turn. F net itself is always pointed toward the black hole. As the star approaches the black hole, the parallel component of the force is in the same direction as the star's momentum. This is because the star is speeding up. After the star passes the black hole and begins to move the other direction, the parallel force also changes direction and causes the star to slow down. What if the black hole were removed and a different black hole replaced it? The new black hole is in the same position and the motion of the star is the same. In this case, if we were to recalculate the mass using the same process, we would find the same value. In conclusion, we have seen the fundamental principles can be used to describe motion, even when we don't know much about what is causing the motion.